Hi guys, it's a guy again, Olumide by name, and today we are gonna be talking and solving another one of the most commonly asked tech interview questions. Today we are gonna be considering the substring anagrams, which is an algorithmic question that is most commonly asked by top tech companies including Google, Amazon, Netflix, Meta, Apple, Microsoft, and other top tech companies. The problem statement states that given two strings S and T, both consisting of lowercase English letters, return the number of substrings in S that are anagrams of T. Well, that problem statement might sound cunning, but what it's trying to tell us is that we need to return the number of anagrams of S that are found in anagrams. We need to return the number of substrings in S that are anagrams of T. And what it takes for a particular substring in S to be an anagram of T is when that substring contains exactly the same letters that is in T, but it can now comes in any order. So what we're trying to say is, let's look straight into this example. We have this example giving us AAB. Okay, let's say we have our string S giving us let me put S here. So we have our string S giving us CAABAB, and we have our T giving us ABA. So now we are asked to find the number of substring of X. Don't forget, when we talk about substring of X, we can have this single letter C to be a substring of X. We can have CA to be a substring. We can have just any extraction of string from this particular set of string or set of characters is a substring. So, and now all we need is a substring of X that contain the same and exactly the same character as T, but in any order. So okay, following that definition, now we see that, look into this, fine, CAA is not an anagram because it doesn't contain the exact character. Why? Because T does not contain C. You understand? The string T does not contain C, it only contains A, B, and A. So because of that, C, AA, or anything that involves C is not going to be an anagram of T. But let's look into another substring of X. Another substring is AAB, and we can see that AAB is an anagram of T because T also contains the letter, exact letter AAB. So we are not dealing with repetition now. So that if a number could contain multiple letters, it is no longer an anagram. It has to contain the same exact set of letters, but it can come in any order. So, and that's why AAB is an anagram. You see that ABA is an anagram as well. So any subset of X that tends to be an anagram of T, we want to sum it up, we want to count them and return that count. That's what this problem is actually asking us to do. Now, for a substring of X to be an anagram of T, that substring, that is in X, for it to be an anagram of T, that substring must actually contain the same length as the length of T. So if T is, like in this case, is of length 3, then the substring we are going to be examining must not pass 3, must not be less than or greater than 3, it must be exact 3. And this therefore saves us the whole trouble of examining every possible substring in X. Don't forget, like I said, a single letter could be a substring of X, just like now C could be a substring, CA could be a substring. So even to count the whole possible substring is too much, it can be much, you understand, and it can even grow with the length of the string. So, but one thing about anagram is that it has to match the length of T. It has to match the length of what we are finding the anagram of. So, and that way it means that we only need to compare the three lengths, or a length that matches the particular T that we are finding the anagram of. So we don't need to care about C alone or CA alone, but we can care about CAA. We can also care about another subcomponent that actually contain 3 letters, like AAB. We can care about ABA. We can care to look or compare BAB and the rest of them, but it must not be less than or greater than the string that we are finding the anagram of. Now that we now understand that really we are not just interested in any substring of x, we are actually interested in substring of x that have the same length as t, that is in this case length 3. So once we have that substring of length 3, we can compare it if it has the same exact character as t. So, and the technique that will be best to solve this problem now is the fixed sliding window technique, because we know that having a window of length 3 and fixed to that length, we can always slide through every possible substring in this particular string s. What I'm trying to say is this right here. The fixed length is 3. Why it is 3 is because the length of t is 3, and then if we're finding an anagram, it definitely have to be the same exact length and exact characters. So, and that's why it is the length is 3 over there. So another thing we'll see right here is that, and fine, let's consider this example here. So we are gonna say that at first we place our left pointer, which means the left boundary of the window, we place it at the first element in the string x, while we place the right pointer at the third element, which is equivalent to our length of t, which represents the length of the string t, which is the anagram we are trying to form. So, and after placing it there, you see that we slide into the string by shifting, expanding and then shrinking at the same time, by shifting the right pointer to the right and also the left pointer to the right, we are able to slide. So you see that as we continue this pattern, we touched every possible substring of length 3 within this particular string s. What I'm trying to say is that, okay, look at the first substring, which contains the first 3 strings CAA, the second substring contains AAB, the third contains ABA, and the last contains BAB. So that is the possible substring of length 3 that you can find within this string. So therefore, using this method that we apply right here is the fixed. Why? Because as we traverse, we actually maintain the length of the window, the size of the window is maintained, and at the same time we get to every possible combinations of length t, that is 3, in the string. So that way now we are gonna check through each of these substrings, the first, the second, the third and the fourth, and we're gonna check any one of them that actually is an anagram of t. You understand? T also is have a length of 3. So anyone that is an anagram is gonna give us ABA. So if you look into the first one, you're gonna see that it's CAA. So it's not an anagram of T. So the second one is AAB, is an anagram, because T is ABA. So it doesn't matter. We are not concerned about the order. We just want to make sure that it contains the same exact letter, and we see that it contains the same exact letter right here, because we have AAB and T is ABA. Similarly here too, we have ABA, so it contains 2A, 1B, and this last one now contains 1A, 2B. It is not an anagram. So these two in between here are anagrams. So you see how fixed sliding window technique can solve this problem. So now let's go in depth into how to apply this, how to solve this really. We are gonna explore this logic using an example. Now before starting the sliding window technique, we need a way to store the frequency of the characters in T. The reason is because, don't forget, anagrams are not concerned about the order of the characters. Whether A comes before B or B comes before A, it doesn't matter. But what really matters is the frequency of each characters. And by comparing the frequency of each characters in a window against the frequency of the characters in the string T, we can determine whether that particular window is an anagram of T or not. So we really need a way of storing the frequency of the string of the characters in the string T. So and we can do this using hash map or an array. So in solving this problem, we are gonna be using an array, so expected frequency array. So and it's gonna be an array of 26 elements, so input 26 numbers, so each of them representing each lowercase English alphabet. Don't forget that we are dealing with string now. The string T is consisting of alphabet which will fall between A to Z. So we are gonna be using an expected frequency array, so that will contain slots, 26 slots for each character of the alphabet. So we have it right here. Our expected frequency, we just cut it down here because we don't want to write ABC to Z. We don't want to create a slot from ABC to Z, and so, but I just try to truncate it right here. So, but if you look at it, let's consider this string T now. You see, T consists of A, B, and A, right? And now, because A comes 2 times, the first A now, we add 1 to the slot for A. A is the first character of the alphabet, so it's the first index in the array. So we have 1 here, but because A comes again another time, it's gonna increment to 2. B comes only once, it's gonna increment to 1, while the remaining one will be set to 0. If there's other character like C or D inside our T, it will also reflect in this expected frequency array. So now this expected frequency array is what we are expecting in a window. We are expecting a similar array of a similar pattern like this for a window to be an anagram of T. Now, to set up a sliding window algorithm, we are going to be defining 3 parameters. So the first one is the left and the right pointer. They are going to be set to the beginning of the string X. Don't forget, we're going to be iterating through the string S, maintaining a window of length 3, because we are dealing with a string T of length 3. So if it's 4, it's gonna be dependent on the length of the string T. So that way now we will try to navigate through the possible sequences in the string X that corresponds to that length. Possible string and sequences in the string S of that length. So, and we're gonna check if it's an anagram. So we'll be having a left and right pointer that we define the boundaries of the windows. You understand? So, and we are gonna also be having the windows frequency. So we are gonna use an array of size 26 to keep track of the frequency of character within the window. Don't forget, we have an expected frequency already that illustrate, and it defines the frequency of the characters in T. The expected frequency is also an array of length 26, and now we are going to be creating a window frequency for each unique window as we transverse the string. So that one too is also going to be of size 26. So and depending on the frequency of the characters in the window, now we are going to be populating it. So we will now be comparing this window's frequency with the expected frequency. So whenever they are equal, we can compare array. So whenever they are equal, then we know that it's an anagram. So we also have the count variable. The count variable is going to help us to maintain a variable count of the number of anagrams. So as we are traversing the array by placing the left and the right boundaries of the windows, we are going to be creating the window frequency to check check the frequency of the characters in the window. And what we're going to do is that we're going to compare that window frequency for each unique window of length T. You understand? We're going to be comparing it with the expected frequency, whether it matches the anagram. So if they are equal, we are going to increase our count by 1 to keep track of the number of anagrams that have been detected so far. Now, don't forget we talk about placing the left and the right pointer at the same position at the very start of the string. So, but before we start to slide, don't forget at the point where we slide, what we are doing is we are expanding and we are shrinking. So the size of the window, the length of the window will remain fixed. And before we start to slide, we need to expand the window, so it could be of the same length as the string t. So and we can do that by expanding, by shifting the right to the right pointer toward the right until it equals that particular length of the string t. So just like we have here now, both of them are pointing at the first element in the string, and what we do is that we shift our right forward to the right by 1, and then we shift it again until it becomes the same length as t, which is 3. So at this point now we can start to compare with the with the window frequency and with the expected frequency now. So okay, right here now, right at the very first one, we actually have our window frequency to be 001. Why? Because both the left and right pointer are pointing at C, and so far we only know of a single character, which is C. So we update that now in our window frequency. Don't forget, window frequency changes while the expected frequency remains the same. So the window frequency have to be updated as the window expands and shrinks. So you understand now. So when we shift our right toward the right by 1, our right pointer toward the right by 1, we come across another string, another character A, and at this point we increment our character in the window frequency by 1, and that's why we are having 101 here. So the first one, representing the first letter of the alphabet, which is A, and the second one, which is B, is 0. Why? Because we've not come across B so far, and as we move on we see C and increment it by 1 as well. So and then we shift our right again the third time, so to the right, I think the second time now. So and we come across an A, and that's why you see A increases by 1. So as we are shifting, we are going to be updating our window frequency, and as we are updating our window frequency, we are going to be comparing with the expected frequency here if they correlate. Look, for instance, now, fine, because the length is 3 now, we can compare with the with our t. You understand? So we can compare the expected frequency with the window frequency, and if we compare, they are not equal because A has a frequency of 2 here, but right here, true, A have a frequency of 2, but B have a frequency of 0 here, and right at this point B have a frequency of 1. So they not correlate, they are not equal. So what we do now is that we shift. We are gonna slide the window by moving the right to the right, the right pointer to the right, and also the left pointer to the right. So to consider another substring of X that is of the same length as T. So don't forget, as we are sliding, we update the window frequency. So we're gonna be going over it now. So right here now, they are up to the length of the window is up to the length of the string T. So it is ripe for comparison. So we're gonna check and compare the window frequency with the expected frequency, and because A have a frequency of 2 in both, fine, but B have a frequency of 1 in the expected frequency, that is, it occur only one time in T, which is the expected frequency, but right here in the window frequency it does not occur at all. We only have a CAA. So because of that, window is not equal to expected frequency, and therefore we continue. And what do we mean by continue? We slide to the next possible subsequence of length T, and this is it right here, by shifting our left and our right toward the right. So we slide efficiently, and don't forget, as we slide, what happened? We left C and we picked B. You understand? So therefore we have to update that inside our window frequency, and you will see that we left C was 1 here, and right now C is 0, and similarly you see B is 1 here, whereas B was 0 here. Similarly, as we can see, B is 1 here, but right here B is 0, so it has been updated. Why? Because during the shifting, during the sliding, although we left C, now we have picked a B within the windows, picked the substring B, and because of that, we now have the window frequency to be 210, where A has the frequency of 2, B has the frequency of 1. And right now, if we compare it with the expected frequency, and right now if we check it with the expected frequency, now we see that they have the exact same set of array, element of array 210 and 210 here. Therefore we found an anagram. We found an anagram. So, but don't forget the problem statement asks us to find the number of anagrams of t that is in x. So we are not stopping right there, we just keep on the count. So what we do again is that we slide on to check if we could find any additional anagram, and what that means is that we'll be shifting as sliding, and right here we are going to appear right here. So we shift again to the right, shifting by expanding the right by 1 and expanding and shrinking the left, or shrinking the window by expanding the left also by 1. So we see that it was AAB right here, and right here is ABA. So what we do now is that, fine, in the process of shifting we lose A, so we're going to be reducing A by 1, but at the same time we gain A here, so therefore it cancels off and the window frequency just remain almost the same, just like before. Why? Because in the process of shifting, though we left this A that was once there right here, that was once there here, but then we shifted to a new A, so it's almost this, it's just the same set of things, AAB, ABA. So, and because of that we found another anagram and we increase our count by 1. So when we perform the final sliding, we are able to leave A again right here, and we attract a B. So that make it well, I'm so sorry about this. This is supposed to be 1 and this is supposed to be 2. So why? Because A is released, 1A is left, so A reduced to 1, and now B is gained in turn, this last B right here. So and we have 1 to 0. So this is not equal to the expected frequency. They are not the same, so we continue, and then that way we are able to loop out of the string, because that's the last substring that we can find there. Now that we have been able to navigate every possible substring of the length t, we are gonna return the count now, and so that's how we solve this problem now. So a small optimization we can apply is that we should return 0 if t is greater than s. If the length of t is greater than s, then we should return 0, because it's not possible to find an anagram of t in s if x is not even equal or greater than t. So it's not gonna be possible. So at that case whereby we can just place it as an edge case, that if s is less than t, we return 0, because there's no way we're gonna find an anagram, so the number of anagrams is gonna be 0. Alright, let's go into the code implementation of the logic that we've discussed so far. We're gonna be calling our function the substring anagrams, and it's gonna be collecting the first string x, which is a string, the second string t, which is also a string. So don't forget s and t. The first one is the larger string that we are trying to extract the anagram t as a substring to s. So, and then the return is the number of anagrams of t that we can find in the substring of x. So it's an integer, that's why I put integer right here. So the return is the number of anagrams that we can find in s. So right now let's deal with the edge case first. Let's collect the length of our s and the length of our t as length of s and length of t. So, and this way we wanna check if length of s is less than length of t. So don't forget, in this case we just return 0, because if where we are trying to extract the anagram from is now lesser than even the anagram we are trying to extract, so it's not possible. So there's now we're gonna find an anagram there, so we just return 0. So, and now we're gonna proceed to define our windows. So the expected, so first expected frequency, so which corresponds to the frequency of the string t, and then our window frequency as we slide through the string s So we are gonna be keeping updating the window frequency. So let's just divide them as an array of 26 elements, so represented initially as 0, so both of them will be of the same length, because we are going to be comparing them to see if they are anagrams. So really, let's define our count as well that we'll be using to count the anagrams. So now we're going to iterate through for each character in T, so that we can populate the expected frequency array. So for each character in C now, we want to take the expected frequency and update odd of C minus odd of A. So once we increment it by 1. So what we're trying to do right here is that actually odd, when we say ORD, odd of A will give us 27, is going to give us 97. So it's just like will I say binary representation or decimal representation of alphabet. Don't forget that every string, every text that you see, they are going to be converted to zeros and ones. So let's say that A and odd of A is going to give us the binary representation of the letter A, something like that. You understand? So, and if odd of A gives us 97, odd of B is gonna give us 98, odd of C is gonna give us 99, and that's it like that. Now, because we are using the expected frequency, we are holding it as an array, and each element of the array, each index corresponds to each character, or let me say each alphabet, each letter in the alphabet. That's why we multiply by 26 here. So each of them, each position, each 0 is representing, a letter in the alphabet, right from A to Z. And so because now odd of A is gonna give us 97, and imagine if the first letter in T is A, just like it is. You understand? So fine, let us write our data. I almost forget that. So S will be C A A B A B, while T is A B A. So if we look at it as we iterate through T, we have A as the first element now, and odd of A, because we're iterating through T here too, so odd of A is gonna give us the same thing, which is 97. So 97 minus 97 gives us 0. So that way we are gonna increment the index 0 in the expected frequency by 1, and that's gonna give us 1. You understand? So that way we can easily target the particular index. If we say odd of B now, odd of B is gonna give us 98. So 98 minus odd of A, which is 97, is gonna give us 1. So we can easily index 1 now, and we are going to be quite sure that it goes on to meet B. You understand? So this is just a way of accessing, by default, odd of something minus odd of something is already 0 based, meaning that odd of A minus odd of A give us 0, odd of B minus odd of A give us 1, odd of C minus odd of A give us 2, and that way you can easily access it in this array that we define to represent the frequency, and that's why we are using the odd. So now that way is going to distribute the frequency and increment them. So all of them is set to 0 by initially, but if as much as the frequency or as much as the letter is occurring inside the string T, is going to be increasing it by 1. So after doing that, now we're going to be defining our left and right pointer. So don't forget they will be at the beginning. So they'll be positioned at the beginning of the string S. That's where we say we're going to position them. So, and because string S, the beginning is 0, is index based. So the first index in the 0, that's where we place our left and our right. And now while right is less than len of S. So why? Because we are going to be expanding and shrinking, and we're going to be sliding, and the end point is when right reach the end of the string. So while right is still less than the length of the string, we can still keep on sliding and doing the sliding technique operations. So while right is less than length, what we want to do is that first of all, let us update our window frequency. You understand? And what I mean by that is that we are gonna add we are gonna increment that particular character at this position, right, which is the first position. Right is 0 right now, so we are gonna go and update it. And how we are gonna update it is by saying odd of s of right. So s of right is gonna target the element at that first position, or at that position that R is referencing, that the pointer R is referencing. So it's gonna go get it, and by the help of odd, so it's gonna get its corresponding index inside window frequency. So it's gonna get it correctly. And what we're gonna do is that, this is a function. Odd is a function. So yeah, so it's gonna get it now. And what we want to do is that we want to increase it by 1, because what we've encountered that particular character inside the window frequency. So we increase it by 1. So now after increasing by 1, we want to check if window frequency is of the same length as the length of the string T. Don't forget that anagram, the first condition is that it must even be of the same length, and we can do that by checking if right minus left plus 1 if is equals to len of T. We already have it as length T. We collect it as length T. So, and what this is trying to say is that, see, okay, imagine that R right is in the position 2, left is in the position 0. Don't forget 0, 1, 2 make 3 already. Now let's look at if this expression is valid. Right is in position 2, left is in position 0. So 2 minus 0 gives us 2, plus 1 gives us 3. You see, 3 is equals to the len of T. So let's say that right is in the position 4 and left is in the position 2. That's 4 minus 2 plus 1, that's still 3. So what this piece is just trying to say is that once the boundaries of the window are sum up to 3, or the boundaries are placed such that the string that is contained within that boundary is 3, definitely it is we should try to check if they are anagram. Why? Because we are sure that now they are up to the length of T, so there's the probability that they are anagram. So, and how we're gonna do that is we're gonna say if window frequency is equals to the expected frequency. So we know they are of the same length. Now I want to know if the characters or the letters are of the same frequency as the expected frequency. So, and if they are, we're gonna increase the count by 1. So, and now we have increased our count by 1. So, but one thing we discuss in the logic is that once they have this, we continue to expand rights up to the point whereby they are of the same length as the length of the string T. Now, once they are up to the length of the string T, we want to keep on sliding and checking if that particular fixed window, just as we slice that particular that window of a fixed length, that particular fixed window, if it is the same thing, if it is an anagram of T. So we are gonna check it. If it is, we are gonna increment the count by 1. If it is not, or even if it is, we are still gonna shift and slide our window toward the right, so as to get as much anagram as possible, or as much possibility as possible. Don't forget the question, the problem statement asks us to return the total number of anagram of T in S. So we are not just counting one and exiting the loop. We want to shift our, we want to slide our window. And now to do that, what we're gonna do is that we're gonna increase our left by 1. So this way now we are shrinking, and then right here we're gonna increase our right by 1 also. So we have efficiently slide this way. But one thing is that don't forget that as we slide, as we even shift our left by 1, we have ignored the last or let me say the first letter in the window. Why? Because we have to shift it. If you go back to the logic we discussed, you will see that in the process of shifting, we are going to drop a character. So because of that, we have to make it to reflect in our window frequency. Don't forget that when we shift our right up here, we make it to reflect by adding by incrementing that particular character, the frequency of that character inside our window frequency. So similarly, if we are going to be shifting our left, we also need to be making it, we also need to make it reflect. And how we're going to do that is that we're going to say window frequency of odd. So this time we're going to be targeting S of left, because S of left is what we reference the particular character that we want to decrease the frequency. Why? Because we are sliding away from it. So we have to target S of left, not S of right, not any random character, but S of left. So minus odd of, sorry, I have this here so it can be tricky, minus odd of A. So this A is a reference point, so that it will ensure that we index that particular element. So, and therefore what I want to do is I want to reduce it by 1. So that's just it, reduce it by 1, and then you can now slide. Don't forget that once we reduce it by 1 like that, so we will reduce it before we update our left. Why? Because we want to remove the current element at that pointer left. So why? Because we are shifting left away from it. So similarly, we added the particular the element at the pointer right before we shift right away from it. And after doing all of this, we are gonna return count. So by the time that the loop exits, by the time right shift, don't forget we are shifting right here, by the time right shift up to the length of the string S, then there's no possibility of finding any more subsets or substring of length 3. Why? Because right, I've even reached the last elements in the string. So we just want to return the count that we have accumulated so far. Okay, so now we want to print our function print substring anagram, passing S and passing T to it. And then we have this. Let's check it out. So right here we have 2 printed out. So this is it, and the answer is 2. Why? Because as you can see right here, AAB is one substring of S that is an anagram of T. So, and then secondly, apart from AAB, we have ABA2, which is another substring of S that is an anagram of C, and that's the whole substring of S that are anagram of T that we could find, just 2. So that's the end of this, and I hope you understand it. You can go through the logic and have a good understanding. Once you can understand the logic, to code won't be the problem at all. So thank you. Do well to like, to comment, to share, repost, engage it in any way you can. Your recruiter, your hiring manager, everyone is actually looking at you. The world is looking at you, because this is social media and you don't know who is watching. So thank you and take care.